Hello, I'm Jovan, and I will present you my work on mManycore, a cloud-native CPU for tail at scale. Microservices are emerging software in the cloud where large monolithic applications are now decomposed into many small, loosely coupled services. Each service implements separate functionality, which brings numerous benefits. Therefore, major cloud providers now rely on microservice architectures. So what makes microservices unique? First, the response time of microservice applications is determined by the slowest service in an application. Thus, we need to focus on improving the tail latency and not only the average. Second, microservices do not use shared memory for communication. Instead, they communicate with each other using remote procedural calls. In these environments, having a chip-wide monolithic cache coherence is often not needed. As microservice requests come in bursts, they need to be queued before executing on cores. Therefore, the design of the queuing system can also impact the tail latency. As services spend majority of their execution time being blocked and waiting on I/O either for the remote storage accesses or synchronous calls to other services, we need to perform frequent context switching. However, even highly specialized software for context switching introduces penalty that is not negligible for microsecond scale services. Finally, microservices issue lots of interconnection network messages due to RPCs and storage accesses. Thus, the contention in the interconnection network can also hurt the tail latency. To address the aforementioned challenges, we propose mManycore, a processor designed for microservices with a key objective to minimize the tail latency of microservice requests. mManycore is designed to minimize the primary overheads that contribute to the tail latency. First, instead of having a monolithic cache coherence, in mManycore we have multiple small cache coherent domains called villages that are not coherent with each other. In this way, we minimize the remote directory and cache accesses and contention. Second, in mManycore, requests are enqueued, dequeued, and scheduled all in hardware. In this way, we reduce the software synchronization and contention overheads. Third, mManycore proposes purely hardware-based context switching scheme to avoid the OS invocations and low-throughput software options. Finally, in mManycore, we propose low latency and high bandwidth on-package hierarchical leaf-spine interconnection network to minimize the in-network contention. The basic unit of mManycore is a hardware cache-coherent village. Multiple villages, a memory pool, and the network hub create a cluster. Finally, mManycore package is composed of many clusters that are connected with a hierarchical leaf-spine interconnection network. mManycore significantly reduces the tail latency of microservices over conventional processors. In this work, we show the imbalance between the emerging microservice environments and current processor design. To address these challenges, we propose mManycore, an architecture optimized for microservice environments that delivers high performance for microservice workloads. Thank you for your attention, and I'm looking forward to the full ISCA presentation.